All right, let me check with the AV guys if I'm ready to go. Yeah? Okay. Good morning, everybody. Thank you so much for joining me here at this session. My name is Molenkamp. This is actually my first time here in Porto. I'm really enjoying it, even though I got really soaked in the rain a couple of times. So the next 60 minutes or so, we're going to talk about Microsoft Orleans, which is a framework for building distributed applications, or at least help you make it easier to build distributed applications. And with these types of technical sessions, I always think it's really helpful to have an example scenario in mind. And my example scenario is going to be based around this thing called the Bokkentocht in Dutch. So what this is an event that's being held at the village where I live. And it is basically a pub crawl. So what you do is you go visit participating bars and restaurants, and you drink beer at those venues, and you get a little snack on the side. And they serve a special type of beer called bakbeer. So imagine my surprise arriving here from the Netherlands, going out into the departure hall at the airport, and seeing all of these signs of Superbak. So this is a very nice beer. I've had a couple last Wednesday. But it's not the type of beer I'm talking about. So this is a typical lager, although they have a couple of variations, I think. They have a red beer and a stout as well. But the type of beer that we drink at these events is a type of beer that originates in Germany. And that started in the 14th century in this village called Einbeck. And they start brewing this beer, and it's a kind of dark, strong lager beer. It's a little bit sweet, and it usually has like a 7%, maybe a bit more alcohol percentage. And then a couple of centuries later, in the 17th century, the Bavarian brewers in Munich, they also started making this recipe. But because of their accent, they started pronouncing it as Einbock instead of Einbeck. So this is where the name bakbeer comes from, and a bak meaning literally a billy coat in English, and that's also why you see a lot of these coats still in the logos on these type of beers. So this is a really fun event. That beer was a seasonal beer. It was typically brewed in the autumn and the spring to align with some of the Christian religion holidays like Christmas and Lent. So in my village we have two of these events. One in the autumn, which is actually taking place this Saturday, so I'm going there straight from the airport, really looking forward to that, and we also have one in spring. Now, I thought, how can we make this already great event even better? Well, I'm a tech nerd, maybe we can write an app for it. So this is what I have in mind. So this is the Bokkentocht app, or the pub crawl app, if you want to be more general. And I'm definitely not an app designer, but bear with me here. So at the top, we could have something like a map showing you all of the events, all of the restaurants and bars that you can visit. And maybe on top of those locations, we can draw a number to indicate how crowded it is at a specific place, so you can decide where you want to go next. And then below that, we can have this leaderboard or ranked list of all the best beers in the venue. So that will help you make some tough decisions about what to order next, because all of these restaurants will serve different types of beers. Now, when you click on a location in the map, that will take you to this second, more detailed page where we can see the venue name, have this big button to check in or check out, and then below that you can see basically the beer menu. So what kind of beers do they serve there, along with some thumbs up and thumbs down icons to rate that beer. Now, if I were to really build this app and use it for the event in my hometown, I could run the backend for this application easily on my laptop, right? It's not a big event. There are maybe 1,000 people, probably even less than that. So this MacBook, it wouldn't break out a sweat running that backend. But we can be a bit more ambitious here. So let's say that instead of just running these tiny puny events, we go for world domination, and we make this into a global multi-tenant SaaS platform to empower all persons all over the world to organize these pub crawl events. So now things are changing, because now at every one time, there could be a lot of these events going on at the same time. And it will probably, my laptop won't be enough anymore to run all of those events, so we need to scale out. So our little app is turning into a distributed system. And that is not necessarily good news, because building distributed systems can be pretty hard. There are a couple of challenges that we'll have to deal with. So I'll list a few on the slide. So first of all, we need to scale this app, but how are we going to scale that in an even way, right? We want an even load across all of those nodes. We don't want to introduce single bottlenecks anywhere. And then if one of those nodes fail, how are we going to deal with that? How are we going to recover gracefully from that scenario? And of course, we have to look at performance. So if you look at scaling out CPU-intensive tasks, that is relatively easy. You can just add more CPUs, add more cores. But what often happens in these kind of scenarios is that the storage layer becomes the bottleneck, so your database gets hit too hard. So there are some ways to deal with that. You could, for instance, introduce Redis, like distributed cache, into your solution. But now we have to think about, how are we going to deal with stale caches and cache invalidation, stuff like that. And then when we have updates on the database coming from different clients connected to different servers, how are we going to deal with that concurrency, make sure that we have a correct concurrent system there? Now, fortunately, and probably this won't come as a surprise, but Orleans can help us solve some of these problems. So what's Orleans? Orleans is a framework for building distributed applications. It originated within Microsoft Research back in 2015, so it's been around for a while. It's been used in the real world in pretty big solutions. Most famously, it's been used in the Halo 4 and 5 video games. And more recently, it was being brought into the .NET team. And they also bumped up the version number, so Orleans was previously on version number 3, but now with the move to .NET, they're at 7 to be aligned with the .NET version numbers. And the big idea here is that they try to abstract away many of the complexities of distributed system, so that we as .NET developers can simply focus on writing our business logic, and we don't have to worry about all the nitty-gritty details going on to face those scalability issues. And it does that using this model called the actor model. But it has some innovations on top of the original actor model, which are really interesting. So before we dive into those innovations, let's take a step back and look at what is the actor model. So the actor model has been around for a while, even longer than Orleans has. It was originally coined in 1973. It was proposed by Carl Hewitt as a model of concurrent computation. So that's a form of computing where a lot of things happen at the same time. So there's a lot of concurrency. And inside the actor model, the primitive that you work with is the actor. And an actor, you can kind of think of it as a distributed object. So it's similar to an object in .NET, but it isn't tied to a single server. It can live on any of the servers in your distributed system. So each actor, you start off by defining your actor types, right? Just like you define classes for objects. So let's say that I want an actor to represent a single participant in an event. So I'm going to call that actor a crawler. And then we can have instances of this crawler type. So let's say Jane is participating in our event. Then that actor has an identity or a key, which is Jane, so that we can address it. The actor can also have some behavior, which is our business logic that we're going to write. And it can optionally have some state, some persistent state. So maybe we want to track where everybody is in this event, and we can store the location inside each actor. That state, by the way, is completely private, so the other actors cannot access it directly, just like you would have a private field inside an object. Now we can have some more instances of this actor type. So we've Bob, Jane, John, and Alice. And then we can also add a different type. So let's add a drinking venue type to represent the drinking venues where we want to go to. So we have two here, the Pubs Up Pub and the Foo Bar. So now how are these actors going to interact with each other? Well, they do that using messaging. So they can send messages to each other. And now something else that pops up is concurrency, because let's say that John and Alice both want to make a call to the drinking venue Foo Bar. Those calls can come in at the same time, And normally you would have to deal with multi-threading and create or use logs or semaphores or stuff like that to make sure your code is correct. But the actor model uses a different way to do that. It uses a turn-based access model or a single-threaded access model. So what happens is that, let's say that Bob wants to check out, and inside that drinking venue actor, we want to keep a counter because we want to know how many people are checked in. So what the actor model will give you is, with this turn-based access model, one of these requests can go first. So let's say Jane is lucky, she can go first. And while Jane's turn is happening, so while the business logic is running to handle that request, the request coming in from Bob is simply blocked, so it's waiting in the queue. And only after Jane's turn has been completed, then Bob gets a chance to run his request, and that will also go through. So this makes it very easy to write a business logic inside that actor, because you don't have to worry about multiple threads running your code at the same time. That makes it really much easier to build correct concurrent logic. So that's very nice. There are a couple of actor model implementations throughout the years. There was I can't remember the name. Does anybody know the name of the first implementation that was still Erlang? Yeah, Erlang. Thank you so much. That was the earliest implementation, and it's still in use today, but it's mostly in the telecommunications sector. Anybody from the telecommunications sector is still using Erlang today? Yeah? Well, maybe. There are a couple of other implementations. On the Java Scala side, we have Akka, and there's also a very nice port called Akka.NET for .NET. And because Akka.NET and Orleans both target .NET developers, I thought it would be nice to look at some of the biggest differences between these two. So Akka.NET is, I would say, a really pure implementation of the actor model. You have a lot of control of when you create your actor, when you destroy it, on which server you want to run your actor, stuff like that. And within Akka.NET framework, all the actors live inside this tree hierarchy, which is called a supervision tree. So at the top here, you have your root actor, which is always there because, hey, the tree needs to have a root. And below that, you have a user actor and a system actor. Now, below the system actor, there are some actors which are used by Akka.NET internally, which we don't have to worry about. But below the user actor, you can start adding your own actor types. So what I've done here, I've added an actor type to represent an event. So we've got event A and B, and below that we have some drinking venues and some crawlers. Now, let's say that we want to check in again. So Jane wants to check into the drinking venue. Now, with Akka.NET, what typically happens is you use tell semantics, so that is one-way messaging. So Jane sends a message to the pub, but it's basically just fire and forget. So what do we do if something goes wrong inside that pub actor, right? Because there's no way in a fire and forget pattern to send back an error to Jane. So what usually happens in Akka.NET is they use this tree to resolve those issues. So if an error occurs in a child actor, the framework will ask the parent actor, so in this case the event A actor, hey, a child just had an error, so what should we do with it? Should we ignore it, or maybe restart it, or there are a couple of strategies, maybe just continue. So event A can decide what should happen, and if event A doesn't know, it can escalate all the way up the tree. Now, if we compare that with Orleans, then first of all, actors in Orleans aren't even called actors, they are called cranes. And Orleans generally tries to abstract away more of the details than Akka.NET. So in Orleans, you don't have to explicitly create or destroy cranes. You can just kind of assume every crane you ever want to call is simply there somewhere. So this is called the virtual actor model. And what happens, these cranes will go through a life cycle. So the first time that you send a request to a crane, you simply think of an ID and you send a request to a crane with that ID. If it doesn't exist yet, then Orleans will create it for you. That is called activating the crane, and it will choose a server to do that on. And it will take care to balance the load across all of the servers. So once your crane is activated, now it's ready to handle requests and it will run its business logic. But then after a while, if there are no more outside requests coming in, this crane can be cleaned up to save some memory. So it will be deactivated by the runtime. But any state that you've stored in while you were working in that crane, that is safely persisted to disk. So the next time this crane is activated, that state will be reloaded from disk and your crane will continue as if nothing has happened. So if you look at messaging in Orleans, that looks much more like just a remote method invocation. So Orleans uses simply async await methods. So if crawler Alice wants to check in into a drinking venue, she simply calls that method on the drinking venue. And now error handling is also much easier because if an error occurs, then the drinking venue can simply send an exception and that can be caught inside the calling crane and you can handle it directly right there. And that even works across servers. So these cranes can be on totally different servers on different sides of the world, and that all that information just serialized and deserialized, and you don't need to worry about it. All right, so maybe just to recap, Akka.NET, I think, is a more pure implementation. It gives you much more control, but it also comes with much more responsibility, right? There are many more different things to manage. Whereas Orleans doesn't give you as much control, but it's really, its model is just so familiar for the .NET developers. It's really easy to get started with. So let's look at some code. Let's see how we can implement this crawler crane. So when you create a new crane type, you start by defining an interface. So here's my iCrawler crane interface. You can see that I derive from iCrane with integer compound key. So every crane type needs to have a key, and there are a couple of different data types you can use for that. You can use a GUID, an integer, or a string, or a combination of a GUID and a string, or integer with a string. Now in this case, I want my crawler crane to represent a single participant within the scope of a single event. So that means I have two parts to my key. I have the event ID, which is an integer, and I have something that represents the user, like a username or an email address, something that's a string. So I use a compound key of an integer with a string. And then also in this interface, I define which methods you can invoke on this crane. So we have a check-in async to check in, and I pass in the drinking venue where we want to check into. And I also have a checkout async method. Now notice these are async await because we may be making network calls, so these methods needs to be asynchronous. Now in this crane, I also want to store some state. I want to remember where I checked in last. So to store that state, I'm just creating this simple container class called crawler crane state. And in that container class, I'm storing the reference to the drinking venue where we are currently located. Okay, moving on to the implementation, you can see my crawler crane must derive from crane as the base class. And then, of course, I also implement my interface. So how are we going to store that state? Well, this is a really simple solution, but it's not applicable to all situations, right? I could just create a private field and now I can store some state. But of course, this won't survive any deactivations because when my crane is deactivated, the garbage collector comes along, throws away my object, and all my state is gone. But in some cases, this may be enough. I'll show you later a dashboard which is created to have a look at your Orleans cluster, and that uses basically private state to just store the state while you're looking at it, and once you refresh, all that state is gone. But it doesn't matter for the use case. But in my case, I really want this state to be persisted on disk safely somewhere. And one way to do that is to use a built-in persistence mechanism that Orleans provides. Now, to use that mechanism, you inject an instance of iPersistent state into your constructor, and you can see I use the state or the container class as the type parameter. And then I have this state object, and on that state object, I have methods to read and write state, very simple. Now, I've also decorated this with a persistent state attribute to give a name to this state, and the reason why I do that is I can inject multiple state parameters inside this constructor, and then you need some way to distinguish between them. You can also use that attribute to specify which kind of underlying data store you want to use to actually store all the bits and bytes. I'm not doing that here, and that means just use whatever is the default. And you can set up the default in your startup code. There are a couple of options. You can use anything that understands ADO.NET. You can use Azure Storage. You can use Cosmos DB, or you can use Amazon DynamoDB. But it's also not very difficult to add your own plugin. And you don't even need to use this iPersistence state. If I want to, let's say I want to use Entity Framework to store my state in a SQL server, I could simply inject a DB context here in this constructor and use that. But I do think it is nice to use this built-in persistence mechanism because it's very easy to switch between different stores, and that makes it easy to use a different data store in your development or test environment than you would do in production. Okay, so now we have a way to read and write data. We can start implementing those methods. So we have our check-in async, and this code is a bit simplified compared to the real code, but it's the core principles are here. So if we want to check in, we can pass in that iDrinking venue crane. And that's a special type of object because it's a reference to the crane, but it's not the crane itself. Because if you think about this, the drinking venue crane that we're referencing may not even exist yet. It may be deactivated, or it may live on an entirely different server. So this is just a proxy object that knows how to find the actual drinking venue crane. And what is really nice about these proxy objects is that they are serializable. So I can store them in my state. It will be serialized. I can come back in a month. I can deserialize it from state, and I can still use that object to call the actual crane. So to check in, I simply take that proxy, that reference, I store it in the state, I call write state async, and everything is safely persistent in the database. And then my checkout method's more of the same, only this time we are simply clearing that current venue field, write the state, and I'm done. All right, so let's have a look at the real code. So I have Visual Studio open here. There are 3 projects in my solution. I have Blazor pubcrawl, which contains the front end. I have Orleans pubcrawl, which is the back end using Orleans. And then I also have this simulator that we are going to use to put some load on the system. Now, if we dive into Orleans pubcrawl, I can show you in the CSPAR file that the only thing you need to get started with Orleans is to add a reference to this Microsoft Orleans server package. And I also added a reference to Orleans dashboard, which is a third-party package, which I'll show you later on if time permits. Very nice to get some insights into your cluster. Then I have this crane folder, and this contains all of my crane implementations. So if we quickly look at this crawler crane, you can see that interface that I've just shown you on the slides. It's a little bit more elaborate here. We also have a method to rate a beer, and we also have a method to get the current status for a crawler. So this will simply return a DTO object, which contains the venue that I'm at and any beer ratings that I've done. And the front end needs this to show your current status. All right, so let's look at the programs, yes, and look at the startup code. Let me, wrong shortcut, let me close this. Okay, so in the startup code, I'm calling builder the host use Orleans to get Orleans up and running. And here I could do some more advanced configuration. So I'm setting up a couple of things. I'm adding the dashboard to my cluster. I also set up localhost clustering. So what that does is when I start multiple instances of the backend process on this single machine, it will create a cluster out of those processes, right? So I can simulate having a real distributed system with multiple nodes on a single laptop. And then I also add memory crane storage as the default storage. So this is for the persistence mechanism, and the type that I'm configuring here is just local memory. So that means whenever you want to write state, just store it in local memory. So when I shut down my cluster, everything will be gone. So that's not something you would use in production, but it's really useful to use for demos and development testing, stuff like that. Then if we scroll down a bit, I have some API calls for the mobile app to call into. And there are two in particular I want to show you. There's one for checking in. Here it is. So this route takes an event ID where we're participating in, and then the venue ID where we want to check into. And if we do a post there, we also get a crawler ID from the header. Now, I didn't bother implementing any authorization or authentication in this sample. So, you know, this in a real-world situation, this could be like a token containing a user ID claim or something like that. But I'm just passing in a string right now. What's also interesting here in this handler is that you can see this iCrane factory. So that's a class provided by Orleans, and you use that to get a reference, so to create those proxy objects to call into other cranes. So to implement the check-in logic, I need to have two cranes, right? I need to have my crawler crane, and I need to have the drinking venue crane. And the crawler crane I can get using the event ID and the crawler ID, and the venue crane I can get using the event ID and the venue ID. And then once I have those references, I can call crawler crane, check in async, and pass in that drinking venue crane where I want to check into. Now, I also have some checks set up inside the cranes to check, hey, this venue where you want to check into, is it even part of this event ID? Because maybe somebody is trying to hack my API. So if that happens, I throw back a venue not available exception, and we can respond with a bad request. Otherwise, everything is fine, and we can continue. Then we have this other endpoint to get the data back out. So this returns that status object that I've just shown you. Very simple endpoint. We just get a reference to the crawler, we ask for the status, and we dump that back to the client. All right, so let's see this running. So I'm going to start the first instance of this backend. And as you can see, this now runs on port 5001. So I'm going to spin up a second node, but this time I'm going to give it an instance ID of 1. And all that does is increment the port number by 1, because I can't have two processes running on the same port number. That doesn't work. So this second one is running on 502. So let's call some endpoints. I have some prepared HTTP statements here. Now the first thing we need to do is we need to create an event, because the system is completely empty right now. And I have a separate endpoint for that. We can post to the events endpoint, and I ask ChatGPT to generate some data for me. So I have a lot of different beers here, not all bock beers though. And we have some venues. So these are the actual venues that I'm going to hopefully visit this Saturday if my plane is not delayed. I have the name of the venue, I have the location of the venue, and I have the type of beers that I serve there. So we can post all of this to that endpoint, and we simply get back an OK, but now we have an event registered in the demo environment. OK, so let's start to call some of those endpoints we've just seen. Let's start by getting the status. Now, obviously, we didn't check in yet, we didn't rate any beer, so this status is still empty. But notice that I went to node number 1, right, which was running on port 501 to get a status. Now let's go to the other node, to server number 2, and check into a venue. So I'm going to check into Herbergian, which is where we usually start. I just get back an OK. So obviously that worked. So now, if we go back to server 1 again and request that status again, it should be updated. And of course this, so you can see it's at Herbergian. So this is a very simple demo, but in fact, it's pretty powerful what's going on here behind the scenes, because we are calling that single crane, which lives on, well, maybe it lives on server number 1 or on server number 2, I don't know. But also, I don't care, because I can reach it from both processes. So it's really a distributed object in that sense. So let me quickly shut this down, do some cleanup here, and then go back to the slide. So what happens, if we visualize this, cranes live in silos. That's another Orleans term, so I just had two processes, two silos. When I created an event, I created a whole bunch of cranes, and they replace automatically in those two processes. And then when I make requests to, let's say, 501, but I want to access Qualla and Molenkamp, which is on a different server, then Orleans takes care of that for me by serializing the request, sending it to the correct server, deserializing it. Now, of course, this does mean if we don't know where the cranes live, then every call to a crane is a potential network call, right? And that will incur some latency in your application. How much latency is kind of dependent on your physical infrastructure, but that is something to be aware about. Now, there are some hints you can give to Orleans on how to place these actors or these cranes. So if there are a lot of events, then we could instruct Orleans to try to keep all of the cranes belonging to a single event on a single node, and that would give us a bit better performance. But what is really nice here is that, let's say that silo 2 goes down, something horrible happens. Now Orleans can step in and simply reactivate those cranes on a different server, right? So we may see a little bit of hiccup in response time, but we don't have to do anything ourselves to fix that. Orleans can simply rebalance those cranes. And of course, when silo 2 comes back online, hopefully sometime in the future, Orleans can also move those cranes back. All right, so let's have a look at the actual app. Now, first off, I do have a confession to make because I wouldn't know where to start building an actual app. So what I did instead was I built a web application. It kind of looks like an app. And I asked ChatGPT again to build me some style sheets in the style of a craft brewery. Now, I'll let you decide if it succeeded, but it kind of used a little bit brownish color, so that's good enough for me. So actually, I have to restart one of these backend processes because otherwise we don't have a backend. And let me start my Blazor server app. That's running on 501. Now if you go there, this is a pretty boring page because it's completely empty because I restarted my backend and I use in-memory storage, so I lost all my actors. So let's very quickly go back, re-add that event. Yep, it was this one. Refresh. And here we are. Let me zoom out just a little bit. So this is my hometown. This is Heilo in the Netherlands, and if we zoom out a bit, you can see it's about 40 kilometers north of Amsterdam. So if you're in the neighborhood this Saturday, I do invite you to join the event. So these are some of the participating restaurants, and let's say we go to one. We can see our overview of the venue. So we have the name, we have the check-in button, so let's check in, and we have the beer menu here. So if I now go back to this page, you can see a little one here because we are checked in there. And of course, if we go to a different place, let's go to this place, check in here, go back, that one jumped to the new place. Here at the bottom, we have the top beers list, but we don't have any ratings yet, so it's still empty, so let's change that. Let's go back in, and well, this is actually the only bugbeer here, so let's pick that one and go back. And now we still don't have any ratings. That's actually deliberate, and I'll explain to you a little bit later. But I can refresh this list. There's a hidden feature. If I click on the title, it does a refresh, and now we do have that rating. So I'll explain later why that is. Let's dive into this whole feature of the rating of beer logic. So let me go here. So how does this work? We have our app. We call into the API to rate a beer. Then the API will find our crawler crane, and it will tell the crane, hey, I want to rate a beer. And the crane will save that rating in its own state, so we can use it later on to display it. But it will also do something else. It will send the rating to a beer score crane. Now the beer score crane represents a score of a single beer in the event, right? So for each beer type, there's a single instance of the beer score crane. And it will collect all of the different ratings, and it can create a total rating for that beer. And when it has a total rating, it sends it to a beer leaderboard crane. So the beer leaderboard is responsible for just keeping the list of the total scores and ordering it in a way that we can ask it for the top 10 beers. But that's one crane in the entire event that does that bookkeeping. So if there are a lot of ratings all flowing into that single actor, then we may overwhelm it with requests and performance will suffer. So what I did here instead is that beer score crane will not directly update the beer leaderboard, but it will only do so periodically with a timer. So that's a pattern that you can use in your own solutions, where if something doesn't need to be updated every millisecond, you can just use that pattern to lower the impact on the system performance. So then finally, when we have that list available in the beer leaderboard, the app can simply go to that crane and ask for the list and display it in the UI. So let's walk through that code. Let me see. Let me clean up some windows here. Let's start with the API. So go back to program. And somewhere down here, yeah, here it is. So to rate a beer, we sent a put request to this URL, which contains the event ID and the beer ID. It also contains, of course, my crawler ID, and it has a rating. And that rating is a simple integer. 1 is thumbs up, -1 is thumbs down, and 0 is, hey, I rated something in the past, but forget about it, just clear it for me. So what we do here, we get the crawler crane, and we tell it, hey, rate a beer. And again, there's some validation built in so that we may get back a beer not available exception, and then we throw out a bad request. So let's jump into this rate beer method. Here it is. So this takes the beer ID and the rating ID. Now, the first thing I want to do here is to validate that this is a valid beer. And for that, I can use this beer selection crane. So that's a crane for which there's one instance for an entire event, and it simply contains the entire beer menu. So I can ask it things like, hey, is this beer available? And if it's not, I can throw that beer not available exception. So now we know that we're good. We can store that rating for this specific beer ID inside the crane, and we can write that to disk. And then the next thing I'm going to do is to tell that beer score crane about this new rating, right? So I can do that by calling update rating, and I give it the crawler ID so it knows where the rating came from, as well as the rating itself. So moving on to that actor, we have the update rating method here. So the first thing I do is I check, hey, did I already have a rating for this crawler? Now, if I do, and the current rating is 0, that means just forget about the previous rating, right? So I remove that from the state. Otherwise, I'm going to check, hey, this new rating, is it any different than the one I already have? Because if it's the same, we can just short circuit this whole thing and return. There's nothing here to change. If we're still here after those checks, and I do have a rating, like a thumbs up or a thumbs down, I store that in state and I write back the state. And notice that in all this code, right, it's turn-based as a single thread. I don't need to worry about other threads coming in and changing state while I'm running this actual code. Okay, so now the beer score crane has the updated rating. It can calculate the total score, and periodically I want to send that total score to the beer leaderboard. So the way I do that is by setting up a timer. Now, there are these lifetime methods that you can use. So on activate async here is called every time your crane is activated. And there are also associated methods like on deactivate, which you can use to do some cleanup just before your crane is deactivated. And in this unactivate, I register a timer. So what I do here, I pass in this crane's object. So I can reference it here as self, because I learned yesterday in Daniel who was at Daniel Marbach's session about performance in Azure SDK? Nobody? Oh, you should replay it on, you should watch it on stream. It was really good. He was talking about closures and memory allocations and stuff like that. And in my previous version, I was just doing this, like report score async. Well, I can type in live demos, but you know what I mean. But of course, then you get a closure because you're referencing something outside of this lambda. So it's better to pass in the object and then use it here, and it will save you memory allocation. So I'm now going to go through all my code and update all of it with his recommendations. So what this does is, this timer fires every 3 seconds, right? So you can specify how long to wait to fire the first time, and then how long to wait before firing each consecutive time. And then when it fires, I'm going to report the score. Now, there are some considerations with timers, because timers are internal to the crane, and that has 2 implications. So first one is that timers don't adhere to the turn-based access model, because the call is coming from inside. And that means it will not keep your crane alive and activated. So if the only thing happening inside your crane is the timer firing periodically, but there are no other requests coming in from the outside, then eventually your crane will be deactivated and also your timer will be stopped. Second implication is that your code may be interleaved with other code executing from outside requests. So there's still a single thread. There are never more than 1 thread running inside the crane, but interleaving may take place, right? So the single thread may run some instructions for your timer callback, and then run a couple of instructions for another request, and then your timer callback again. So that's really something to be aware of when you are working with timers, especially if you are mutating state inside your timer callbacks. Now there is another mechanism called reminders. And reminders are external to the crane, and that means that they do use their turn-based access model, so they will keep your crane alive. So generally, those are a bit more elegant to work with, but they're also more heavyweight. So you wouldn't want to use reminders for any events that occur more than maybe a couple of minutes. These timers are really better suited for those high-frequency events. Although you can combine, of course, those different patterns, right? You can set up a timer and then maybe also set up a reminder in the background to make sure that your crane stays alive by firing a reminder to it every couple of minutes. All right, so let's look at the report score. What do we do here? We calculate the score. We do a double check. Hey, is this score any different than the last score that I reported? Because otherwise there's nothing news to tell. And then we get a reference to the leaderboard crane, and we tell the leaderboard crane, hey, here's an updated score for this beer ID. So let's jump to that final crane. Update score. So this is pretty simple crane here. It's only like 40 lines of code. It has some state to store the scores with simply a dictionary of the beer ID and the score. And then we have these 2 methods. So we have a method to get all the top beers, where we do some link, which also is pretty bad for performance, I learned yesterday, which takes the top 10 beers. And then we have update score to update the database. And this is what's called in Orleans as the smart caching pattern, where we basically use the crane as a kind of a hot state. Because any query that we get for those top 10 beers, we don't need to go to the database. We can serve the answers straight from memory here, right? We only need to go to the database whenever we want to make an update. And we can even go further than that. If we want to lessen the load on the database even more, we could say, hey, whenever a score is updated, we are only going to write the actual data back to the database every minute or something like that. But of course, you know, it depends. It highly depends on your situation, because if anything happens to that crane in the meantime, you will lose those changes. All right, so yeah, I think that's all the code I wanted to show you. So let me, well, let's go back for another feature, and then I'll show you the app working with some more data. So let's look at the feature of checking in and showing those numbers on the map. So this is going to look pretty much the same as the previous slide. So again, we have the app, we do a call to the API, the API will find our crawler crane, it will tell it, hey, I want to check in, the crawler crane can save the location inside the crane state, and then we add the crawler to the drinking venue. So now the drinking venue crane knows which crawlers are currently there, and they can keep count of those crawlers. And then once in a while, again using that same timer pattern, that crawler count is being sent to an event map actor, our crane. And that event map is responsible for keeping all the data that I need to show that map in the front end. But there's an additional feature request here. So I want that map to update in real time. Right? I don't want the user to need to refresh all the time to see the numbers change. So we need some way to push that data from that crane to those clients. And for that, I'm going to use SignalR Hub. So any people here already familiar with SignalR Hub? Yeah, I guess most of you. So yeah, this is a messaging framework which you can use to send data from the server to connected clients. It uses WebSockets, and if WebSockets aren't available, it can gracefully go down to things like long polling, stuff like that. So what will happen is we can create SignalR hubs, which are basically the pipeline between the server and the client, on all of the nodes, and then the clients can connect to those hubs, and they can receive the data. So that's pretty sweet and easy to set up. We can create our own hub by deriving from hub, and then we go to the startup code, we register an endpoint so that the clients have something to connect to, and our hub is ready to go. But now we have this next problem, because we have a crane, which is Orleans aware, it's running on one of the nodes, and it needs to be able to use those SignalR hubs, which are on different nodes. And how does it even know which SignalR hubs are there? Now, Orleans can fortunately help us with this by a very nice feature called observers. And observers are basically the clue codes between your cranes and your regular .NET objects. So you can use it to send messages from your Orleans cranes to ordinary .NET objects. So the way this works is that you first define an interface to basically define what kind of message you want to send to the .NET object. And that interface must derive from iCrane observer. So here I've created a send venue attendance updated async method. And of course that must be asynchronous again, because we are crossing server boundaries. And my message will contain an event ID, a venue ID, and the updated attendance number. And then we can implement, we can create an object that implements that interface, or a class that implements it. And in the constructor, I inject a iHub context for the SignalR hub, so I can send messages. So whenever that send venue attendance update async method is called, I use that context to actually send a message to all of the clients. So that's nice, but now I still need a way to create those observer objects. And I still need a way to let the event map crane know which observer objects there are. So to do that, I've created an observer servers object, which is running on each of the nodes. And in that servers, I'm going to use the crane factory to create the observers. So now we've used the crane factory before to create a proxy object to a crane, but you can also use it to create a proxy object to an observer. So here I have the hub context, I wrap my event map observer object around it, and I ask Orleans, hey, give me a proxy object that I can pass around throughout all of my cluster, but still be able to call that .NET object. And once I have that, I can give that proxy object, that reference, to another crane called an observer list, and now the event map can once in a while ask or query that observer list for the complete list of observers. So I think I do that like every minute or so in case there are any changes. And then whenever it's time to push out an update to the clients, I can simply iterate over all of those observers and call venue attendance updated. So a message will go to each of Signal or hubs, and then it will go out to all of the clients. So that's how that works. And let me show you that in action. So let's see, my this is my front end still running, my back end was still running. So let's start the simulator to put some load on the system. So I can add a max crawler count to specify how many simulated crawlers I want to have. And this simulator I also built using Orleans. So I have two types of cranes in there. I have a simulated event and I have a simulated crawler type. So the simulated event will just simply spin up pretty slowly crawlers until this maximum. And then each crawler will pick out a venue, check in, drink some beers, do some ratings, check out, go to the next venue. So when I run this and go back, and yep, here you see those numbers changing. So this will slowly ramp up to 1,000 crawlers, and it's pretty evenly distributed. So we'll probably end up with around 200 in each venue, and then you will see some slight variations of people moving to different venues. All right, so we can also refresh the top beers. You can see that my scoring algorithm isn't that random. I tried my best, but it's still a demo, so I thought, it's fine. All right, so I do have some time to show you that dashboard. So if I go to, I believe it's running on 8080. Yeah. So here's that third-party dashboard. This is really useful for debugging your applications because it shows you stuff like, hey, methods with most exceptions, and it's methods with highest latency. So this is really interesting to see how your Orleans cluster is behaving. It is pretty heavy though to run, so don't run it continuously in production, but use it on like a test environment to see how your application is doing. We can look at a crane activation. So we ask for 1,000 simulations, right? So we have 1,000 crawler cranes here. You can see that we have 15 of those beer score cranes because we have 15 types of beers, and we have a couple of singletons here like the event map and beer selection. And you can also see this dashboard crane here because this Orleans dashboard itself is also built using Orleans, of course. It's Orleans all the way down, and that just queries the Orleans APIs pretty often to be able to render all these metrics. So yeah, that is really useful stuff. All right, so let's go back to the slides to wrap this all up. So we've seen what Orleans can do, but unfortunately, building a distributed system is still kind of hard. Orleans and the actor model in general are definitely no silver bullets. You still need to really think about how you are going to design your system. But it does make it easier, especially if you're in a situation where you can model your problem domain as a lot of small entities working together. And if there's a lot of concurrency of those entities, then Orleans can really help you with this. We are currently implementing a project for a metering company in the electricity sector where we model basically every meter as a crane, and then when data comes in we need to do validation, and we can keep that a lot of data like what was the last value that we saw and what are the highest and lowest numbers. We can keep that in the hot state inside the crane, so we can do those validations very quickly. So that's a nice example of a real world scenario. Of course, Orleans can really help us with that scalability because it will basically take care of placing all those cranes for us, and it can also help us to gracefully recover whenever one of our nodes crash. And if you look at performance, we've seen that smart cache pattern where you work with those hot states, but it's also really important that whenever we do get updates, they all go through that single crane, and that's very nice because it's very easy to build your business logic and to make sure it's still correct in a concurrent way. So overall, I really like Orleans. I also think it's pretty easy to get into once you know a little bit of .NET because it's really designed to be familiar for the .NET these developers. So with that, thank you very much for coming to my session. If you want to have a look at the source code, it's all up in my GitHub repository. I also am the host, together with a buddy of mine, of Netflix, which is a video channel on YouTube where we talk about Microsoft, Molenkamp, stuff like that, other related things, so you might enjoy that as well. So with that, thank you so much, and I think we have a couple of minutes left if there are any questions. And if you can't think of anything right now, I'll be here for a couple of minutes, and you can find me all around the conference. We do have one question. Yeah. Yes. Yeah. So the question is, how memory hungry is all of this? The overhead is pretty low, so it kind of depends on how much are you going to store inside your cranes, right? So if you have, if you look at the documentation, what the team says is you can basically have millions and millions of cranes as long as only a subset of those cranes is active at the same time. Right? Because all of your deactivated cranes, they don't take up any RAM, they only take up space somewhere in a database. So it is something to be aware of when you're designing systems like this, because if you have a lot of cranes that are all active at the same time, you need to have the server memory to be able to use that. Yeah. If you look at my example scenario, there can be like millions and millions of events that happened in the past and are going to happen in the future, but aren't active now, and that's okay. And maybe there are like, I don't know, a couple of hundred events that are active right now and that are currently using cranes, then that will probably be fine from a memory perspective. Yeah.
Hi, I have a question about the data, let's say consistency.
Mm-hmm.
We saw that the crawler venue has been updated, and you say the state of the crawler, and then you send the message.
And
the count was updated. So how I don't know, durable this messaging is, and how do we achieve the consistency of the state and the count?
Yeah, that's a very good question, because there's no transaction around that, right? So what happens if you've saved something in your crane state, but you also want to send out a message or call another crane? So basically, you're on your own to solve that. Orleans doesn't really give you a built-in mechanism to do that. What I mainly use is retries. So in this case, it isn't really applicable to this demo, because in this demo, of course, there's a user. So if, as a user, I click check-in and it fails, or only half goes through, and the user doesn't ever click retry or check-in again, then I'm screwed. But in the real-world system that we're currently building, we have a message queue in between. So that message gets handled, and we just make sure that everything we do in the crane is idempotent. So we expect the message to arrive at least once, but probably multiple times. So eventually, we will proceed by, we will succeed in both saving the state and sending the message to the other crane, and everything will be fine eventually. But it's something you have to take care of in your design. Yeah.
Just to understand the messaging between, you mentioned that you are using some message broker. So it is kind of so you can set up to use some messaging. For example, when you send the message, it's some internal messaging communication, or it uses some message broker.
Yeah, so the message, it's not using a message broker. It's basically a task that is, you can basically compare it to a remote method call. That's just taking a long time if it's queued. So let's say your cluster goes down. All of the messages that were in transit will be gone. There's no underlying persistent message queue. So the message broker I was talking about in previous answer is in front of the Orleans system, so that if something happens in Orleans, I can replay it from that message queue. Yeah.
I also have a question. So if we have, for example, a system that is geographically distributed, and for example, in a region A we have like 10 nodes, on the region B we have 10 nodes, so will it try to rebalance itself based on a latency and store objects inside region like A, if, for example, initially an object was instantiated in a region B? Or is it possible to configure?
Yeah, so by default it will try to rebalance. It will try to get to a even load, right? So it will look at the cranes and how much resources they use and try to distribute on top of that. If you have some specific needs on how you want that balancing to occur, you can configure that. I don't know all of the details by heart, but there are options, hints that you can give to Orleans on how to configure that. So you may want to have some cranes in region A, some other cranes in region B, or maybe just make sure that 50% of the crane types are always in A and the other 15 is always in B.
What I was keeping in mind is, for example, we have an event that is happening in region A, for example, and there is no event in a faraway location in a region B. So if the system will try to distribute load automatically, like in equal way, then, for example, we have a high load in a region A, but we don't want object to be stored in a region B because it will be a very big latency between those regions.
Yeah. Yeah, so if you have, if your cluster consists of servers where there's a lot of latency between them, you want to give hints, so keep it in A or B. But then, of course, if you lose an entire region, it can still reactivate all those cranes in the other region. And then the question becomes, okay, but will that region be overloaded because all of the people will now go to that region? But that's really dependent on your specific situation. Yeah.
Okay.
Okay, thank you. All right, so thank you very much, and enjoy the last couple of sessions here at NDC.
And if you could all please remember to evaluate the session with the cards. Thank you very much.
Oh, okay, great. Yeah. 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 Mm-hmm. Yeah, there is you you go to the Azure website and you do need